Okay, hello everyone and welcome to our final inviter talk of the conference. It is my pleasure to introduce our speaker, Pascal Becher, who I'm sure really needs no introduction in the ICAPS community. Very well-known researcher, lots of papers at ICAPS. So he is an associate professor at the Australian National University, where he's held various positions since 2021. Prior to that, he spent 10 years at Ulm University, where he did his PhD with Susanna Biundo, and then coordinated a technology transfer project doing AI companions for home improvement. And before that, like many of the great researchers at ICAPS, he started his studies at the University of Freiburg. He's very well known for his work on hierarchical task network planning. As you'll see, he's going to talk about today, partial order causal link planning, and on model repair. He does complexity analysis, algorithm design, but also through his work on modeling, kind of bridging the gap between classical planning and application. He is the winner of many awards, and this is why I've got a big list here. I couldn't remember them all. So he won all 5 tracks of the 2023 HTN planning competition in which he participated. He won the ICAPS 2019 Best Dissertation Award. He has 2 Best Student Papers at ICAPS, including this year's award, and 2 Best Undergraduate Student Papers at ICAPS, which I think is really a testament to the fact that not only is he a great researcher, but also a great mentor for the next generation. He's also won Best Paper at ICTIME and Best Student Paper at SOX 2024. He's also a great community member. He has no fewer than 7 awards for outstanding reviewing. And he's known not only for his great work, but for his great paper titles. He has many good ones, including his Best Student Paper title this year, which begins, I always told my mum order is overrated, for a paper about the complexity of unordered HTN planning. He told me over dinner the other night that his metric for seeing if a problem is interesting enough to solve is if he can explain it well to his mum. So without further ado, I will hand over to Pascal to do his inviter talk. Thank you very much.
Hi, buddy. Thank you so much for inviting me and for your kind words. And before I start, I have to make a disclaimer. Actually, I beat Daniel with his own planner to cite him from my talk that he gave. So the true winner of the IPC, I think, is actually colleague, which is also true for a lot of papers that I was involved in. So I'm very unfortunate that I have a great team. And my declared goal of today is to maybe not expand the team, but to expand the people working on hierarchical planning. So I hope that over the next few years, like a third of the audience will consider to start working on hierarchical planning for at least one paper or another. So that's actually what I'm trying to achieve here. That's why I call the talk an invitation. So let's start. What is hierarchical planning? I would like to start with a disclaimer. First, hierarchical planning can be many different things. And I will focus on a very specific formalism, HTN planning. There's more to hierarchical planning than just that. For example, you can define a hierarchy upon your state variables. There's a formalism called hierarchical goal networks, and there are many others. But I will focus on HTN planning. More specifically, the formalism that I built my work on is more or less the same that was introduced already in '94 and was so influential that also ICAPS gave them an honorable mention for the most influential paper award, and I believe very well deserved. One more disclaimer until I finally say something more technical, that even when I speak either here or my papers about HTN planning isn't HTN planning. So even within HTN planning, there are many different formalisms, and the one that I'm focusing on today is the most simplistic one. So I gave an analogy that non-hierarchical planning, there's a lot of work, right, with time, uncertainty, maybe not uncertainty, but time. There's a lot of things you can do. And for hierarchical planning, that's obviously the same, and it's also the same for HTN planning. And the formalism I present today is the most simplistic form of it, but there are still many extensions. Now, in this HTN formalism that I'll focus on today, the idea is that you start with an initial compound task, and your domain model gives you standard recipes, standard rules on how you can implement that compound task. So in this sequence of pictures that you see, these white little boxes are compound tasks. They are abstractions of more primitive tasks. And these filled boxes, they are the actions that we all love. And so the lines on the left and on the right, they just depict their preconditions and effects. And so what you do in hierarchical planning is that you start with an initial compound task. You look up in your declarative model which ways to make it more primitive exist. You choose one, you apply it, you obtain a new task network, the one in the middle, for example. You get more compound tasks, you look up how they can be refined further, and you continue the process, you continue and continue, until at the end, eventually, you found your primitive task network for which you want to find a linearization that is executable, as everybody knows, and achieves a goal description, a goal state. An example of that is to obtain your PhD, which many people here have, others are still working on it. And as you see, that's actually super easy because you only need 3 actions. You do research, you write your thesis, you defend it, done, very easy. In reality, however, it's of course much harder because each of these actions, actually not actions, they're compound tasks, so they need to be refined further. But this is a great way of abstracting what you're doing on higher levels of abstraction so that you can more easily grasp what you want to do. Now, I don't think that I need to describe block-worlds to you, and I'm also not saying that we need HTN planning so that we can finally solve block-worlds, but it's very nice to explain the basics. So in classical planning, not hierarchical, everything that you want to plan for is expressed in terms of states. So your actions must specify all the criteria under which an action is applicable and how it changes the state. And the goal that you want to achieve is also fully described in terms of a state, in terms of a goal description. In hierarchical planning, you can do that differently. You plan for activities. So for example, if you want a block to be clear, which means that there's nothing on top, then you can declare a compound task, make clear. And we will see 2 decomposition methods for that. The first says do nothing, just chill. When can you do this? You can do this when the task is already achieved. When is the task of making a block clear already achieved? If in your current state it happens to be clear already. In this case, a valid implementation is doing nothing. The task disappears. There is a recursive rule as well, the one-step rule, where if it's not clear, there must be another block on top of it. So if the precondition is satisfied that another block is on top of your current block, then you can choose this method, which recursively breaks the task down. So then you have first to make this block on top of you clear, and then you can unstack it from your current block, put this down to the ground, and you have implemented your task, but well, you have just introduced a new subtask. So you continue to do this, and here is an example trace. So if we want to make the block C clear, we cannot use the left method because C isn't clear yet in the initial state, so we have to choose the right method. This turns it into this plan, so we've decomposed this compound task, but now make clear B is yet another compound task that's not allowed, so we need to choose a method. The empty method is still not a choice. So we choose again the right method, turn it into that, and now the compound task make clear A can actually be decomposed into the empty task network because in the initial state, A is actually clear. So we can now decompose this into the empty task network, and we are done because now we have a primitive task sequence that is executable. If you look more closely at this example, then you see that now suddenly we have saved some predicates. We don't need gripper free anymore, and we don't need holding anymore, because we know that they're satisfied, because we know exactly where we are in the task hierarchy. Because it's like, you just know that unstack is always executable because you're strictly following that hierarchy. And therefore you need less information to put into the state because it's like magically included into the hierarchy. Now, a little bit more math. This is how it's usually explained, even in papers. Hierarchical planning is usually explained as this hierarchical way of problem solving. But I claim it's actually a different kind of problem, and this definition here shows a little bit clearer how you can define it. So we now decompose the solution criteria by first looking at the induced classical planning problem. So we're interested in the set of solutions for an HTN planning problem, but for that we first throw away the hierarchy and just look at the induced classical planning problem. So look at the primitive action set and ignore all the methods and compound tasks and just look at the solutions to the induced classical problem. That's one bit. Now we can do the same for the hierarchy. Let's set all the facts, all the state variables to the empty set, so every plan will be executable. And now also ignore the goal, I mean, it's empty anyway because there are no facts, and concentrate on all the action sequences that you can reach via the hierarchy. So you just look at the HTN as a formal grammar and look at what's reachable in the refinement space. And now, if you have these two sub-solution sets, I hope that most of the audience already sees where this is going. We can now define the solution to an HTN planning problem as the intersection of the induced classical planning problem plus all the action sequences, the primitive ones, that are reachable from your task hierarchy given your initial compound task. And this gives a very clear, I believe, a very beautiful view of what HTN planning problems actually are. And that is that it's nothing else than putting a filter on top of classical planning problems. That's really it. Take your classical planning problem, define a task hierarchy, and the task hierarchy throws out some undesired actions. That is it. So if you forget everything, this is what you should keep. Now, what are possible motivations for doing research or applying HTN planning? Why should you care about a filter to pick out some otherwise regarded solutions, even though they're executable and make the goals true? Why would you want that? So these are not my answers. They're just collected from the literature and from tons of discussions and papers, obviously. So I think the most traditional one that especially a lot of people who are not working on hierarchical planning still share is that it's for search control and scalability. So the underlying idea here is that you're still thinking of your problem as a classical planning problem. So you put everything in the state, and your state also describes all the properties that you want. So that's the classical view of solving a classical planning problem. You want to reach a state, but you want to do that quickly. And so what you can do is to introduce a task hierarchy to guide the search, so that hopefully if your hierarchy is designed in a clever way, you're ruling out some solutions which might technically be executable, but they don't make much sense. And maybe you're also walking to the solution slightly more quickly because the hierarchy guides you. So that's something that many people do. And this is clearly the advice view. You want kind of semantically to solve a classical problem, but you want to do it more efficiently. So that would be advice. And the grammar filter is just a technical means to do this. It's not a dogmatic purpose by itself. And yeah, the question, does it work? Yes. If you compare classical planners with a non-equivalent HTN model that focuses on specific solutions, then usually you're quicker. There are several papers which have shown that. But paradoxically, even though the idea here is to make it easier, the mechanics that HTN planning introduces makes it computationally harder. I have a short slide on that, but I think that's kind of an accident. Now, personally, I think this is by far the most important motivation behind HTN planning. And disclaimer, they're not mutually exclusive. You can kind of combine all of them. So if you ask a domain expert, not your standard PhD student who wants to create a benchmark so that they can test their planner, but go to an actual domain expert. In so many cases, the model is given hierarchically. They are not telling you, oh, you need these 27 preconditions and these 10 effects. They're probably not going to say that. They will certainly say that for the most important things, but it's more likely, I believe, and I've heard that in many conversations and seen that in papers, that they just think of the problem in such a rule-like way. Oh, I need to do this. And in order to do this, I first do that, and then that. And maybe before that, also this. So this to achieve X, first Y, then Z. And that is basically a decomposition method. And my point here is that I believe you should always model your problem in the way that your knowledge is currently available. So if you're a domain expert and you think of your problem in a hierarchical manner, then it makes sense to write it down in that way. Even if you could also model it classically, as long as you have efficient planners available. Now, by modeling it hierarchically, you also have some advantages, but clearly also some disadvantages. In Bloxwell, we saw that we were actually needing only half of the predicates. We didn't need all of them anymore because they were just not required because of the hierarchy. So modeling might be easier because you use the hierarchy. On the other hand, the downside is that, well, now you need to make sure that the hierarchy actually allows you to express and find exactly the solutions that you're interested in. So you're exchanging one against the other. So you have to make sure that the hierarchy is working properly. But yeah, there's also some work that helps you in modeling your problems. But yeah, there could be more, so join. Now, another motivation is to have more control over the desired action plans. That's not quite the same as the advice page that I had, that you want to find solutions more efficiently, but this really takes the stance of saying we can exploit the grammar to express the solutions that we want. And you can look at this both theoretically and practically. Theoretically, you can look at all the solutions that you can express. For example, the planning problem solution set a to the power of n, b to the power of n, where a and b is an action, which means action A has to be executed exactly as often as action B. That is a trivial context-free language, and therefore obviously is a trivial HTN problem, and you could just describe that. Whether your application actually needs this is another question, but if you have such structures that you can naturally express using a grammar, then HTN planning might be a good choice. And also you see already, well, there's an n involved, so you're counting. You have to make sure that action A is applied as often as action B. That's accounting. Even though in the formalism I presented, there are no numbers. We just have propositional state variables, and it still works because of the grammar restriction. And such a language would not be expressible with classical planning because they only have the expressivity of regular languages, and everybody knows that this is not a regular language. But yeah, that's the theoretical side. But personally, I believe the practical viewpoint is so much more important. And that is that those solutions that you want your domain to be able to express might, in certain applications, just be easier to express if you have a hierarchy. I also have an example that luckily Amanda had already teased. So I was working together with other colleagues, many actually, while I was still back in Ulm. Although we just published our most recent work weeks ago, a journal article summarizing all the empirical findings with our user studies. And in this project, we worked with Robert Bosch GmbH and put together an intelligent assistant that helps a DIY, a do-it-yourself handyman, in putting together hobby projects. Think of a bird nesting box or maybe a key rack where you can put your keys on. Any small hobby projects that involve wood and therefore various operations on the wood, like cutting it in half, sawing it, drilling into it, and so on. And in this project, we wanted to create an intelligent assistant. That's an actual running system that you see over here that not only knows how the project is to be implemented, so which steps are involved in order to create the project that you have in mind, like a key rack or bird nesting box. But beyond that, the assistant also knew all the devices. This is, of course, where Robert Bosch came into play. So we could tell the users exactly how to use these devices to achieve exactly the project they're working on. So depending on the kind of wood, they use exactly the right saw blade. And what was very important for Bosch over here was, of course, safety, because clearly if you actually deliver an intelligent assistant for your own project and somebody cuts their their fingers off, that's not good publicity. And so it was really important that we had full control over the action plans presented. And since all these devices usually come with instruction manuals anyways, hierarchical planning was really the right choice here because it was quite easy to just follow the steps from the instructions. Doesn't mean that computationally you need that expressive power, but that's my point. It's just convenient if you can follow these courses of actions that these experts knew already. And then because it's an HTN, you know that this is going to be strictly followed as long as the user does what they're being told. And here it was, so to give an example, whenever you exchange a saw blade, you actually see that here, you have to take out the battery just to make sure that really nothing can happen. And of course, that might also be expressible with a precondition, yes, but it was still quite canonical to follow all these instructions that tell you exactly the sequence of steps that you need to follow. There's another feature of this assistant that we were able to exploit because we were doing hierarchical planning, but I talk about that in a minute. So another application is plan explanation and visualization. Think again about this plan. It wasn't even fully meant as a joke because you could model it that way somehow. But I was nevertheless being able to explain this on these higher levels of abstraction, and I could do that because it's a hierarchical model. And this is, of course, also true for other applications, for example, like the one I just showed. So in our assistant, we actually had only 2 levels of abstraction. It was just a prototype, it's just a few people working on. But of course, if you put more time in, then you can have multiple levels of abstraction. And what we could do here is that we have these instructions that the user is being shown on either a higher level of abstraction for experts or for people like me, I have no idea what I'm doing there. It would be very atomic. So it's really very detailed, telling exactly where to click and what to do. And the user was then able to change on which level of abstraction he or she wants to navigate and to follow these instructions. So you could either just remain on the topmost level, or for some step where you felt more insecure, you could refine and go to the deeper level of abstraction, while the underlying planner makes sure that everything works. And yeah, that's also a standard motivation that you see all the time for people actually deploying this technology. But for the sake of completeness, because I do not want to preach that everybody should do HTN planning, I want to preach that you should choose the best formalism for your application at hand. There is a very nice work, I believe, that shows how you can show classical plans also on higher levels of abstraction, although the problem was not solved via an HTN model. But they still provided a hierarchical model of the problem so that you solve an underlying classical planning problem. So you cannot save preconditions and effects because of the hierarchy. You still need to put everything into the states. But because you still have a hierarchical model, instead of showing your 33,000 actions from yesterday we had a talk, you can use this technology and show it on higher levels of abstraction, which is also possible. But you still would need a hierarchical model for that. Now, a last one that I also believe is important. This is, again, work by Daniel, that if you want to do plan recognition, then you might have a hypothesis of what your agents actually do. Physically, in the primitive action model that has been modeled, lots of different actions and therefore plans are possible. But you might have an idea of what an agent that you're being observing, what their goals might be. And this can then be expressed in plan libraries. So this plan recognition formally means you're observing certain actions, and you either want to know what is the remaining actions that are still going to follow. So what else is this agent going to execute in the future based on what you have observed? And maybe what's actually the high-level goal that this agent pursues? What's the state that he wants to achieve, or the higher-level plan that he wants to execute? And if you have hypotheses in terms of a plan library, that's just naturally an HTN. A plan library like this category or this list of hypotheses of what an agent might possibly pursue, you can model that as an HTN. And what you see here is a small example that Jean can tell you more about. So this is work by her. in which this was used to monitor a pilot based on the sensory data so that we know what exactly they're doing, like landing or whatnot, so that we can also intervene if we see that the plan is changed. And that's another example because we know the different subroutines for a certain high-level task that somebody is going to do. Now, I want to quickly talk about solving hierarchical planning problems. There is also, like in non-hierarchical planning, obviously a huge range of possible algorithms to solve planning problems. And one of the most prominent ones, or at least in the more early ages of hierarchical planning and planning in general, is plan-based search. So there are many planners. UMCP again, there was the paper that also created this formalism for HTN planning that is in a variant still used today, was doing plan-based search. And in plan-based search, every search node is in the states. It's a complete plan, like with everything. You're not progressing anything array that we will see later. But the entire state, the entire task network is in your current search network, and therefore they just grow and grow and grow and grow until at the very end, you have a super huge final task network or final search node that you know is being executable. Most approaches here use partial order causal link planning. And here, I think I hinted at that in the beginning. Compound tasks in the formalism I introduced are just names, nothing else. They're just used for their refinement rules, for the decomposition methods. But in these plan space approaches, you very often find an extension to HTN planning where even compound tasks show preconditions and effects, and they are then usually used to insert causal links that are a technical means to make sure that a plan is executable. And yeah, the Panda planner here is also one of the probably more famous ones that has also been developed at Ulm, my former affiliation. We have many compilations. For example, yeah, I mean, the usual one, right? All the constraint programming, SATs, we have many different compilations to various variants of planning, and also by really different teams. If you wonder about the kind of, even though they're all kind of different teams, they are heavily overlapping. But there are really a lot of different teams that work on these different things. And so if you're an expert in any of these technologies or in yet another technology and you think, hey, wait, there isn't an HTN planner yet that deploys this technology to solve problems, there you go. Maybe you can transfer it and we get yet another solver for this. Now, the most well-known, I believe, way of solving hierarchical planning problems builds on the system SHOP. So SHOP is from 1999, and what it does, it's very close to classical planning. We see that in the slide. So in 1 minute. And there are many different planners that build exactly on that. So that's also very highly influential planning system with many different variants by different kinds of teams. So I'm quickly going to explain how this works in just 1 minute. So in HTN planning via progression search, you also start with your initial task network. Originally, I told you there's only an initial compound task, but that can be compiled away. That's not a big difference. So it's kind of the same thing. So in here, you see a partially ordered task network with one primitive task in the beginning. You could, however, also decompose the compound task C first, and only once you're completely done with both A and C, then you can continue with B. And the way this works is just a standard search, for example, using A star. And here you have 3 options. Because the horizon basically touches either the A or the C, you could apply A and then progress away the state, making the task network smaller, or you could leave the A where it is and instead decompose C and use one of the methods that you see at the top right. And so this is basically how progression search works. Just take the next thing and apply it, decompose a task or execute an action. And so they grow and grow and grow until you've progressed away all the primitive tasks and have reached the goal state. Now, this is the most easy way to explain how it works. Just a note that you can do it a little bit more cleverly. Daniel has some work in JAIR and ICAPS 18 to show how you can make the search space slightly smaller without actually losing a solution. So that's not exactly how you would do it, but that captures the main idea. Now the question, why am I showing this? Because this is not a tutorial, right? This is an invited talk. So why am I explaining something that's technical? Well, remember the title of the talk, an invitation. My declared goal is that over the next few years, a significant percentage of you considers, maybe I can transform my technology to the HTN planning community. And so what you might have seen here, if you were paying attention, is that you could transfer many techniques from classical planning to hierarchical planning, especially in the search algorithm, because this is basically state-based search. The main difference here between this and standard classical planning search is that you also have to deal with a task network. So yes, you do have a final goal, but you're also restricted with regard to the action set that you can deploy. So in the first task network, for example, you only have, so the CB, you only have the actions available that can still be reached from C and B, and you even know that the actions from B must be executed before the actions from B. So the C actions have been executed before the B actions. That's an additional constraint, and if your heuristics or pruning techniques can exploit that, your search will be more informed. And the same for the other two task networks. It's clearly obvious that the reachable action set in those two task networks are different. Besides, what if you don't have a goal? HTN planning is also computationally expressive if you don't even provide a goal state. What do your classical planning heuristics do then? So that's a very interesting scenario to develop pruning techniques or heuristics. And it's still very close to classical planning, as you all know. You just need to get in these grammar constraints. Now, since most people here in the room are working on non-hierarchical planning, which here I call classical, I want to point out a little bit more of the similarities and differences. And what I've both read in papers and also gotten from conversations from people at the conference is the claim that HTN planning is incomplete. And so I want to say a few words about that. First, I believe completeness is not a property of a problem class. I believe it's a property of an algorithm. So an algorithm is complete if and only if it can find all solutions to the problem. Or maybe you can define weaker notions, like if the problem is solvable, your algorithm can find at least one solution. Or you can say it finds all solutions, all optimal solutions, or maybe at least one optimal solution. They're different notions. But it's a relation between the problem's solution set and the solutions that your algorithm can actually find. So we can ask, are HTN planners complete? The answer is very obvious, is yes. Almost every single one of them is complete. However, I have, as I find, a super cool paper at ICAPS last year, where Mohammad, one of my PhD students, proved that even if you have a perfect heuristic, and even if you're operating in a significantly restricted special case, which is totally ordered HTN planning, computationally much easier than the general case, even then, A star is incomplete, even when solutions exist. So literally, there are solutions. You have literally the perfect solutions. You have a totally ordered task network problem. A star can get stuck in an infinite loop, doesn't escape, even though there's a solution. That's because decomposition methods don't incur costs. They are just free task network manipulations. They're not increasing the cost value. But there is hope. We have shown that you can normalize your problem and then all is good again. You are complete again. Let's come to the important question. Is the HTN formalism complete? And I say, what does that mean? How can a formalism be complete? Like, what would you compare it to? But here, the obvious answer is, well, we can compare it to classical planning. So is HTN planning complete compared to classical planning? And maybe the first answer that comes to mind is, well, no, obviously not. We want to use a grammar to kick out solutions. That's the whole point. But yeah, of course, if you kick out solutions, then they're gone, and therefore you're losing something. So in that sense, you are incomplete, but that's exactly why we were doing it. We want to restrict the solution set by a grammar so that we are artificially declaring executable action sequences, not as solutions, to reject them on purpose. However, we can look even more closely at that. So we could ask the question, yes, HTN planning was defined that way so that we can reject certain solutions, even though they are executable and make the goals true. But what if we want to exclude fewer solutions? Can we still do something about that? Because I've mentioned earlier that defining a task hierarchy might not be that easy because you cannot rely only on the preconditions and effects. You must make sure that this recursive structure of hierarchy does actually allow you to find everything you might potentially be interested in. And there we have this already very old result that for every single classical planning problem, there exists an HTN planning problem that has exactly the same solution set. So if you're saying HTN planning is incomplete, you cannot find everything, I say, no, you can. You just need to model it appropriately. The proof is actually entirely trivial. That's it. That's the entire proof. So you need only one compound task. I've called it the insertion task. And for every action in your primitive action model, you have a decomposition method that inserts that action, followed by a compound task. And that way, because it's recursive, you can simulate arbitrary action insertion. So for every single action sequence that you could possibly think of, there is a path through this recursive decomposition process that creates exactly that action sequence. And whenever you want to stop, so whenever you want to finish creating your action sequence, you can choose the leftmost decomposition method, which decomposes it into an empty one, and then you're done. And so with this encoding here, you can generate, using HTN technology, every possible action sequence. Although this is probably not the best hierarchy that you can use to illustrate actions on higher levels of abstraction, right? That's just a technical, mechanical instrument over here. There's no real semantics behind. But it proves that if you're actually interested in arbitrary, complete task insertion, you can also do that using hierarchical planning. So if you're afraid that parts of your hierarchical model might be harder to model using a task hierarchy, it might be so much better to be modeled using classical planning. This is your answer, because this is basically classical planning. So the two implications that we have here is, the formalism itself is not incomplete, because if you want arbitrary action insertion, you can just use this little trick and insert it. And another implication is that you could even combine HTN planning with classical planning if you want. So even if you have an application that is intrinsically hierarchical and you create your hierarchical model, if there are certain parts that you would like to model in a classical fashion, you could just use this insertion task and put it into exactly that bit where you want to insert actions. And you are then even slightly more powerful because you can say which actions to insert in which parts. Because this model here is given in advance, it's written by hand. And therefore, if you have your hierarchical model, you could put one insertion task on the very left and the other one on the very right, and they might use different sets of primitive actions. And so you have even more control of which actions are being inserted arbitrarily. Now, as Amanda already said, I have quite an amount of work on theoretical investigations in planning. So let me just quickly, I will not go into the details, highlight a few key milestone results. Also because it touches the question, okay, we've just seen that hierarchical planning can model every classical planning problem, but can we model even more in case we have more complex constraints? partially we answered that already because we saw the language a to the power of n, b to the power of n, which cannot be modeled, at least not with numbers, without numbers. But if you restrict to the computational complexity, then these are 3 milestone results. One, that in the totally ordered setting, that was basically the blocks world example, you can model exponential time complete problems. And if you restrict to an arbitrary partial order, then you're undecidable. And a very novel result, Amanda mentioned that as well, it's by Pascal Lauer. He has shown that when your decomposition methods don't actually contain any ordering constraints, it's literally just a multiset where you say, you have to do all of that, but please figure out the order by yourself. So if you don't even support the concept of an ordering constraint, but you still, of course, want to find an executable linearization at the end, then hierarchical planning, which I now have just termed no order HTN planning for consistency, then it's p-space complete, which means you are exactly as computational complex as classical planning, but you still have these benefits of having a hierarchical structure that you can exploit for, well, all these examples that I gave. And there are many restrictions. For example, if you have only one compound task, you maintain decidability again. That's by Maurice Decker and Briga Binke, also both here. You can eliminate recursion, or you could, as everybody here knows, just ignore delete effects. But if you ignore delete effects, it's still NP complete. So it's still a very expensive framework. There's one formalism that I also pushed towards that's related to the last slide. I've termed this HTN planning with task insertion, where you can arbitrarily insert primitive actions. So it inherits, again, this criterion of refining hierarchically, but just like in classical planning, you can always insert every primitive action whenever you want. It's basically the same thing as the compilation that I said, that I introduced one slide earlier. If you do that, you don't need recursion anymore. So basically, whenever you declare a TI HTN planning problem and it's recursive, then the recursion is kind of pointless because you could otherwise rely on task insertion. And therefore, it's also easier computationally. Now, as said, I was hoping that a few people here in the room might actually consider to apply HTN planning for their application or transfer their own technology to the hierarchical setting. And so you have survived the technical part. This is just a little bit of infrastructure that the community has. If you think, oh no, that's the first time I've ever heard about HTN planning, how should I start working in that field? Hell no. This is my answer to that. So we have a description language, HDL, which is really the canonical extension of PDDL, because we are subsuming PDDL. The only thing that HTN planning adds are these decomposition methods. So that's basically it. So everybody that can read PDDL can already read HDL. And it's published, so you can just use it. What's also very convenient is that we have a parser for it, and it's both a standalone program that you can use for your applications, but it's also in the Visual Code marketplace that you can just install. I think it works very well. We have had already 2 planning competitions, and I hope that we will have another one very soon. That said, for the sake of completeness, Michael's very happy about that. There were already 2 earlier HTN planning competitions, but they had a different flavor. These are the traditional planning competitions of you have to deal with an arbitrary HDL model, solve it as quickly or as good as possible. The earlier 2 IPCs were, there's your model, design your own hierarchy as advice to get it solved quickly. Not the same thing. We have an annual workshop. I have founded it together with many others, obviously, in 2018. So we already had the 9th edition this year. And thank you for everybody who has webied here before. And a warning, we regularly invite non-HTN experts to get them into our community. So you might also get an email at some point. And we really have exceptionally high review quality. And I think you heard the talk yesterday that ICAPS does already have an absolutely exceptional review quality. And HPlan is also mind-blowing. We make sure that every paper has at least 3 reviews. And we tried that the majority of reviewers has at most one paper. So the feedback that you receive is stunning. So you can just submit to HPlan, and that will also help you improve your work. We have a mailing list. You could be the subscriber number 100. If so, shoot me an email. And there's a webpage, hierarchical.net. It's basically a hobby project, but I try to be complete. And there are lots of planners listed, basically all the technology that there is, so that you can start using the stuff for your own applications or prove that your technology is better than the one already produced. Problem class-wise, I said in the beginning, I showed basically simple task network planning, but there's a huge range of variety. There's HTN planning with time. There's HTN planning with uncertainty. That's also something that I'm recently pushing towards. There is what some people call hybrid planning with preconditions and effects at compound tasks, also huge field. Dana now has planning and acting, where you have control structures, basically the programs that you can execute. So, and there's much more. You can learn HTNs, you can repair failed plans, you can repair faulty models. As Amanda said, that's also something that I'm working on. And of course, so much more. In principle, every single research question, obviously, that exists in non-hierarchical planning clearly exists there as well. And for sure, there are some people that would like to use HTN planning technology. So if you're an expert in your subdiscipline, you could just say, okay, I will transfer that to the HTN community so they have it available too. That brings me to the conclusion. I was showing several motivations for HTN planning. They are now ordered in the order that I believe they're most important. So I think the most important reason for HTN planning is not the computational complexity or whatever. It's because your domain expert might think of your model in a hierarchical way, and they might have these hierarchical structures available. And then you can model it that way. You have more control over solutions. That's the filter view. So you can express your constraints in a grammar-like fashion. You can display your solutions on higher levels of abstraction and use that for explanations or displaying solutions. You can use it for plan and goal recognition. And yeah, maybe you can also use it for scalability. I don't mind much. I think we have cool heuristics for that. But if that makes your planner more efficient and efficiency is really important for you, then sure, you can do this as well. Task hierarchies, that was the main catch line that I had in the very beginning. Restrict the set of solutions, but unfortunately, this also makes it harder than normal planning. Okay, I see a few smiling faces. Sorry for the pun. And with this, I end. There are so many research directions. Everything in classical planning can be transferred. Maybe it's already there, but even if, then you can make it stronger. As always, that's research. Or maybe something just doesn't even exist yet. And in this case, just bring it to that community. With that, I close. Thank you for the audience for not running away and listening to me. Thank you for inviting me. And thanks for a good chunk of my HTN co-authors. I did not have space for all of them. I apologize. Thank you.
Yeah. Hi, sorry, I've sent the microphones off before this, but thank you, Pascal, for a great talk. Adi has just asked me to announce, please don't leave before the end of the questions because he has a very important announcement. But with that, I will open the floor to questions.
Who selects? Is the microphone actually?
Thanks, Pascal. Very interesting talk.
Thanks.
Here. Yes. And I can attest firsthand to the high quality of reviews at HPlan. I mean, I was blown away. I was so surprised. But I want to ask a different question. So if you consider robots that need to act autonomously, right? One of the arguments that we tend to make about using classical planning, right, is that you model the physics of the problem, and then if the robot encounters an unexpected situation, right, then it can generate a new plan from the state that happens to reach.
Yep.
And if you have an HTN, then even though there might be a plan in the physics, it might not be part of the HTN constraints. So how can you handle something like that?
Excellent question, and this is actually an extremely complicated question, which is exactly why last year ICAPS gave out the honorable mention for the best student paper award. Is it here? Maybe it's here. Yes, it's here, paper number 5. To a work that compares different repair models to see how that is being done. So, I mean, there are different algorithms, and you just need to be very careful of what the intention behind your model is. Are you actually using the hierarchy to model not advice, but to model physics? Think of Bloch's world. We were actually throwing away 2 predicates, and the model was still correct. And why was that? That's because we knew where we were during the execution. So the hierarchy was actually not advice. In this example, it was physics. And in that case, you must remain in the task hierarchy. Otherwise, you're losing information. But it really depends on how you're using the model. So there are approaches that can do vPlan just from that state. And they basically surveyed all the different repair approaches, which do notably not just differ in their algorithms, but much more importantly, in the semantics of the problem that they do. So I can't say more because it's a very difficult question, but that's my answer, that you have to be careful what your model means, what the semantics is, and based on the semantics of your model, you have to choose the right repair approach. But for that, I think their paper is the perfect entry point.
Thank you, Pascal, for very interesting talk and discussion. So you characterize HTN planning as classical planning plus a grammar or a filter for the solutions. So a complementary approach would be to use a classical planning extended or enriched with the temporal logics. So, for example, we started with PDI3, but now we can handle the full linear temporal logic and pure past linear temporal logic. So I was wondering, it would be interesting to investigate a bit further the relationship between these 2 approaches along more dimensions like expressiveness, knowledge engineering, algorithms, and possibly hybrid approaches. Have you something to say about this?
So in ICAPS 22 with Song Chuan, we have looked at the power of LTL, as you say, and strips with LTL or HTN with LTL to restrict solution sets. And there we showed that even when you use these temporally extended goals, HTNs can still express more. That's simply because LTL still only operates on the state space, and therefore it still can only express regular structures. But a context-free grammar, and that's essentially what a hierarchical task network does, or the hierarchy of it does, can simply express more. But personally, I believe one isn't better or worse than the other. But as mentioned earlier, I believe you should choose the technology that most naturally expresses what you want to express. So if the constraints that you have on top of your solutions can very naturally be expressed as an LTL formula, that might either be over the state sequences or even over the set of action traces. I have a paper at ICAPS this year too. Very cool talk, should come tomorrow in the complexity session. Then you should do that too. It really depends on what is the most natural way to express the constraints that you have. But purely explicitity-wise, HTNs can do more. But I would certainly not use HTNs if the most canonical way of expressing your constraints on a solution set should be done using temporally expanded goals on the state, right? And of course, I would choose that.
Computationally speaking, in terms of also algorithms, there was also dissertation thesis on this, where you can compile many constraints into classical planning and then use classical planners. So this is another dimension that should be considered.
Yes, there is a lot of work on that. So both one Alfred, Daniel Hüller, and Gregor Behnke, they have done, and also other teams, they've done lots of work of compilations. They have especially done into classical planning, but there are, I think I mentioned this, where was it, solving? So there are many different compilation techniques and also especially into planning. So yeah, there is ongoing work, but there can be more, of course. And this is also, if I can make one more round of promotion, this is also where I think complexity investigations are really helpful, because both heuristics as well as compilations into other planning formalisms, they have often been motivated by certain classes that were discovered to make planning decidable. And then these results were turned into compilation techniques.
Thank you, Pascal. So if we look at planning as sequential decision making, so essentially we work with sequential data, right?
Mhm.
And that level of abstraction, clearly there are other problems which could be characterized similarly, right? Like working with time series data, etc. Forecasting and other problems, right? Could we borrow some of the techniques that are developed in HTNs to attack other problems that we work with sequential data?
Excellent question. What I was wondering is, it's a very abstract question, but I started saying that you might identify that you're already an expert in a certain subfield, which just hasn't been studied yet in HTNs because our community is so much smaller. So why not bring it to there? But the other direction might be true, because if you're working in HTNs, you just automatically, you have to think of the problems in terms of formal grammar theory and automata theory. It's just naturally happening, I believe. And I think if you're developing this view on formal grammars, then I wouldn't be surprised if you might also discover some technologies that come from that area and put it back into classical planning or non-hierarchical planning, even though they don't have hierarchical constraints. But they still have a DFA, right? State transition system is basically just a DFA. And so I'm just absolutely saying I could imagine that some of the insights that an HTN expert has, because they're thinking about grammars all day and night, that they could be transferred back to classical planning. But more precisely, I probably had to think a little bit longer about this.
Yeah, so I really enjoyed kind of the relationship that you gave between kind of classical planning, right, and a more classical form of HTN planning. If you look at kind of when HTNs emerged, right, it was a very popular paradigm in the 70s and the 80s, right? I mean, 94 was a formalization, but it had been really popular beforehand.
Yeah.
And the reason why people had been pursuing HTNs is because in the real world problems, they wanted to deal with time, quantity, uncertainty. They wanted to do design structures as well as actions and stuff like that. And to be able to deal with those problem features, they needed to be able to reduce, right, the candidate space.
Yep.
Okay. When we present HTNs in the classical setting, right, then you don't get part of the motivation, which was to have a much richer representation. So can you say more about what the advances have been made when you talk about HTNs with temporal constraints, policy constraints, hybrid, numeric, and the likes?
I'm probably not the right expert for that exact question, but I want to stress that what I presented was the most simplistic form of it, but that's also because I've done the most work there. And I think it also makes sense to present the most simplistic basics to get started. But all these extensions that you're talking about, they're not just buried in the 70s, they still exist. Areas, for example, is a planner that supports both time as well as numeric planning. Is that true? Where is it? So there are planners which are still rich in that regard. Aris is one of them. Cydex, I believe, also has either time or temporal. You have to look into this. So there are modern planners that still do support these higher level features. I've just restricted to the more simplistic form over here, but they do exist. And everything here could also be extended therefore, which again was even proven in these other systems. I've just not been working on them myself.
One last question. Do you have the microphone?
Thank you. Yeah.
Yeah, thanks for the talk. So I'm a user of planning and of classical planning and interested in optimal plans, but I could definitely see myself putting on some hierarchy to kind of control or guide the search. But now my main question would be, are there conditions that I can easily check to know that I did not lose my last optimal plan? I don't think you have.
Yeah.
anything yet.
Yeah, it's a question. I actually got asked this question in the past before. So we do not have an explicit optimality verifier yet, but optimality verifier is nothing else than a combination of a plan verifier of the solution that's supposed to be optimal plus a non-solution or bounded non-solution verifier, right? That you say there does not exist a solution up to length n, and we don't explicitly have solvers yet that focus on either optimality proving or on disproving plan existence up to a bound, but planners that have this skill still exist. For example, if you take a SAT-based HTN planner where you bound the length of the plan, then you can, after you've verified the optimality of your solution, check that the other one is unsolvable. And I just realized that the ICAPS paper I have here on modeling support on a constraint network to, or constraint language to repair, oh wait, that's classical planning. Okay, so it does not exist yet, but it's not impossible to do this, which is another reason why more people should join the field.
Okay, thank you. Let's thank Pascal again.